Hi, I'm Kathy. In this lesson, we're going to look at logarithmic functions. Our specific objectives are graphs of logarithmic functions, applying earlier work to logarithmic functions, and a logarithmic model. Let's begin our discussion of logarithms by connecting them to exponential functions. Suppose we want to find the inverse of the function f of x equal a to the x. Now, a to the x is a one-to-one function, so it has an inverse function. What we do is replace f of x with y to begin, then interchange x and y to get to the inverse. Remember, they have their ordered pairs in reverse order. And now, to solve for y, I need a function that will represent the fact that y is the exponent on a that gives me x. And that function is written log base a of x. Again, I want to indicate that this means that y is the exponent on a that will result in x. The inverse function for f of x equal a to the x is this function. Using inverse function notation, we say f inverse of x is log base a of x. Notice the base of the exponential function and the base of the logarithmic function are the same. Well, let's put in some numbers and graph an exponential function and its inverse. What we want to do is graph the function y equal 2 to the x and the function y equal log base 2 of x. We'll do that by making tables of values starting here with 2 to the x. If x is negative 2 in this function, I find 2 to the negative 2, which is 0.25. 2 to the negative 1 is 0.5. 2 to the 0 is 1. 2 to the 1 is 2. 2 squared is 4. Now, what I know about a function and its inverse is that their ordered pairs are in reverse order. So to get the ordered pairs for the inverse, I'm going to reverse the ones I just found. 0.25 negative 2. 0.5 negative 1, 1, 0, 2, 1, 4, 2. And now I'm going to graph both of these and compare their graphs in the same coordinate system. So first we want to graph 2 to the x. It contained things like negative 2.25, negative 1.5, 0, 1, 1, 2, 2, 4. And if I connect those with a smooth curve, I have the graph of 2 to the x. Now I want to graph the other function, log base 2 of x. Now it contained 0.25, negative 2, 0.5, negative 1, 1, 0, 2, 1, 4, 2. And if I connect those points with a smooth curve, I get the graph of the inverse of the original, which is log base 2 of x. Notice that the graphs look like pairs of inverses in that they look like reflections about the line y equal x. Well, let's take a little bit of time to discuss the logarithmic function's graph. We have a logarithmic function, f of x equal log base a of x, where a is greater than 1, like the one we just did, where a was 2. The domain of that is 0 to infinity, and here's a graph similar to the one we just drew, domain 0 to infinity. The range is negative infinity to positive infinity. And notice these points. The function contains a to the negative 1, negative 1, 1, 0, and a1. Well, there's some more information that I want to indicate about this. For f of x equal log base a of x, where a is bigger than 1, it's increasing and continuous on its entire domain, and you saw that as we graphed. The y-axis is a vertical asymptote as x approaches 0 from the right, and I'd like to point that out to you since that's the first time I've mentioned that. Notice that the y-axis is a vertical asymptote as x approaches 0 from the right. And finally, for this particular graph, the graph goes through the points a to the negative 1, negative 1, 1, 0, and a1. Well, what about logarithmic functions where the base is between 0 and 1? Let's look at that. Suppose f of x equals log base a of x, but a is a number between 0 and 1, a fraction less than 1, I should say. Here's a picture of a graph of a function of this type. The domain is 0 to infinity, as it was a minute ago. The range is negative infinity to infinity. Notice the points labeled on the graph, and let's summarize that. I should point out, though, we still have this y-axis acting as a vertical asymptote. Continuing with this, for this function where a is between 0 and 1, this function is decreasing and continuous on its entire domain. The y-axis is a vertical asymptote as x approaches 0 from the right, and the graph goes through the points a1, 1, 0, and a to the negative 1, negative 1. Well, let's use some of this information to work an example. What we want to do is graph the function y equal log base 2 of x minus 1. We want to give the domain, range, asymptote, and x-intercept of the function and tell whether it is increasing or decreasing on its domain. Well, we graphed log base 2 of x. This is a shift of log base 2 of x 1 unit to the right. What happens is the vertical asymptote moves from the y-axis to the line x equal 1. But since all that's done is a shift of the graph 1 unit to the right, we know that the graph of the function is going to look roughly like that. It's going to contain this point, which is the point 2, 0. So let's write down the domain of the function is 1 to infinity because the vertical asymptote shifted 1 unit over, or the whole graph shifted 1 unit to the right. The range of the function didn't change. It's negative infinity to infinity. The asymptote is the line x equal 1. The x-intercept is the point 2, 0. Well, why don't you try one like this? What I want you to do is pause the video and work the following problem, then restart it when you're ready to check your work. Here's what I want you to do. Graph the function, give the domain, range, asymptote, and x-intercept, and tell whether it's increasing or decreasing on its domain. Pause the video and try this. Well, let's see how you did. Again, we're working with the logarithmic function log base 2 of x. This plus 1 is going to shift the function up 1 unit, and the 3 is going to cause a vertical stretch of the logarithmic function. But there is no horizontal shift, so the y-axis is going to stay the vertical asymptote. But the point that was originally at 1, 0 is now going to be at 1, 1. Remember, there's a vertical shift of 1, and there's a horizontal stretch of 3. So we should be sure to draw the graph stretched horizontally. Let me label this point and write down the domain, which is 0 to infinity. Write down the range, which is negative infinity to infinity. Write down the vertical asymptote, which is the y-axis, or the line x equals 0. Write down the x-intercept. Now we need to think about that for just a minute. The x-intercept is where this hits the x-axis, or where y is 0. If you put y equal to 0 here and subtract 1 and divide by 3, you'll see that the x-intercept is the point 2 to the negative 1/3, 0, and on a calculator that's about 0.790. And finally, this function is increasing on its entire domain. Let's look at another example that has to do with connecting exponential functions and logarithmic functions. Here's what we want to do. For the exponential function f of x equal negative 10 to the x plus 4, we want to find f inverse, then graph both f and f inverse in the same viewing window. Well, as we began this lesson, let's start by putting in a y for f of x, then switching x and y, and now we got to solve for y. I'll start by subtracting 4, multiplying each side by negative 1, and what that will do to the left is change the signs of both terms. And now if I want to solve for y, y has to be expressed as the exponent I would attach to 10 that would give me 4 minus x. We write that y equal log base 10 of 4 minus x. It's common to write a log base 10 without writing the 10, just writing the letters log. Now this is the inverse of f, and so I need to indicate that by writing f inverse of x equals log 4 minus x. So I found f inverse, and now I want to graph f of x and f inverse of x in the same viewing window. Well, let's look at a calculator and do that. So on our calculator, we'll put in negative 10 to the x power plus 4, and on your calculator find your log base 10 button, and inside it put 4 minus x. Now as far as a viewing window, what we have set right now is negative 5, 5. Let's extend that to negative 8, 8 with a scale of 1, negative 8, 8 with a scale of 1 in the y direction, and look at a graph. What we see are the exponential function and then its logarithm, both graphed. What I think I'll do is show you that they're inverses by graphing a third function, the line y equal x, and you'll see that that cuts right through their point of intersection. And you are to understand that the calculator's physical capabilities are limited on graphing that logarithm. Well, let's continue by looking at a logarithmic model. The function defined by f of x equals 27 plus 1.105 log of x plus 1 approximates the barometric pressure in inches of mercury at a distance of x miles from the eye of a typical hurricane. Let me point out right away that this log, when you don't see a base, is log base 10. The first thing we want to do with this model is approximate the pressure 9 miles from the eye of a hurricane. We're going to take the function and evaluate it at 9. So we'll find 27 plus 1.105 log of 10. You may use your calculator if you like, but log base 10 of 10 is 1, and so this is going to be 27 plus 1.105, which is 28.105. And so this is the barometric pressure in inches of mercury 9 miles from the eye of a hurricane. Let's use our model and answer another question. This question says the ordered pair 99.29.21 belongs to this function. What information does it convey? Well, the x-coordinate is the number of miles from the eye of the hurricane. So 99 miles from the eye of the hurricane. The barometric pressure is 29.21 inches of mercury. Well, in this lesson, we've done a number of things with logarithmic functions. Be sure to work lots of exercises from your textbook for practice.